Okay, so for 4.4, we're kind of expanding the ideas of quadratics into physical situations. And what we'll find is within these physical situations, there will ultimately be two equations that we're searching for. One equation will be used to substitute in for one of the variables in the other equation. So again, we'll have two equations. One of those two equations we want to create a function out of, like a quadratic function. And that equation will be represented in two variables. So the first equation, we will be able to solve for one of those variables in terms of the other and then substitute in. That's our overall goal. And in order to accomplish this, one thing most likely in all of these, drawing a picture, and that we're going to assign variables to key quantities like perimeter, length, a point, and so on. Label other quantities, the length of this is 20 meters long, etc. Write the two equations and then substitute one equation into the other. So my thought on this, the way I like to attack these problems, and these problems are going to be challenging, some of them are, and it's just going to require work and trying more problems. And the more you do, the more comfortable you get with it. But if we have this framework of two equations and using one equation to find one of the variables in terms of the other and then substituting in, I think that's a good model. So as we look at number one, it says the perimeter of a rectangle is 100 feet. So we have the perimeter of a rectangle, and then we want to express the area of the rectangle in terms of x. So they tell us what function we want in terms of x, and that's the area. So I'm going to write two equations. I know perimeter equals 2L plus 2W, and I'm going to make it x and y, x being the length or width, and then y being the other. And then the other is area, and we know if x and y are the areas, or excuse me, are the sides, then the area would be x times y. So if we want to express the area over here as a function of x, that means a of x equals, we want this equation right here just in terms of x. So that's one of our equations, that the one that tells us we want in terms of x, that's the one we're trying to create a function. And the other one is the one we use to get y, because we want area in terms of x, we want to solve for y in terms of x. Well, what other information do we have here, which is labeling other key quantities? We know the perimeter is 100. Now note I didn't draw a diagram on this, and we certainly could, and we know what that would look like for a rectangle. Now, here's the thing. I want the area just in terms of x, but right now I have it in terms of x and y. So the logic is, if I can get this equation, y by itself, I know what y will equal in terms of x, and then I could substitute in. So if we do that, solving for y, we would subtract 2x from both sides. So we get 100 minus 2x equals 2y. Divide by 2, and we get 50 minus x equals y. And now we know that y equals 50 minus x. And I'm just going to give myself more space here. Now we have x times y, but y again is 50 minus x. And now I can distribute that. X times 50 would give us 50x minus x squared. And now we have the area of the figure in terms of x. What does that mean? Well, it would be a parabola facing upside down. So that means as x increases, the area would get larger, and then it get to a maximum point. If x gets too large, it would then decrease. That's something we can talk more about as we move forward in class with these. Next, let P be point xy on the graph y equals root x. So I think it would be beneficial to draw out the graph root x, which looks something like this. And then it says express the point P to the point, look at that point, the word got cut off a little in the copy over to this app, to the point 1, 0. So if I graph the coordinate 1, 0, that's the point right here. And we want to know a point on the graph in general, p comma xy, but I'm going to make my life easier, similar to what we did in the last unit was with average rate of change, I'm going to make y equal to root x. And there's actually our substitution already. There's like that first equation. Our first equation is y root x, and we substituted root x in for y. So we want to, all we're doing is expressing the distance between these 2 points. Now p can vary. P can vary somewhere along this curve, and then the distance would change based on where that point is, which is based on x. And of course y is determined by root x. So we want the distance formula. The distance formula, but instead of writing it as d, I'm going to write it and expressing it as a function. F of x is the square root of x2 minus x1 squared plus y2 minus y1 squared. So x1, I'm going to do the x minus 1. That's easier than doing 1 minus x. And then for y, I'm going to do root x minus 0. And now what we're going to do is simplify this. So the first part, if I distribute out the x minus 1 times x minus 1, that would give us x squared minus 2x plus 1. And now this part right here, this is just root x, because root x minus 0 is root x, and root x squared, the root and the square cancel, and we're just simply left with x. And now we can simplify it. We get root x squared minus x plus 1, and look at that. That is actually the function that we dealt with yesterday, the root of a quadratic. And then we know how to work with that in terms of minimizing finding the vertex, which would be minimizing it. So if we wanted to find the point on here that was, and this is looking forward as we into the next section, we could use the negative b over 2a on this function to find the point on this curve that's closest to that, if that was our goal. Okay, now we're going to come across what are called wire problems, where we have a wire, and again, draw a diagram that's a length of x, and is bent into a circle. So first off, x would be the length of the wire, and then it is bent into a circle, which then tells you that the perimeter or the circumference of the circle is x. So I'm actually going to write that x equals 2 pi r. There's one equation. And now the second equation, because that, again, c equals 2 pi r is circumference of the circle. We can actually talk in class why it's 2 pi r rather than just being given by mathematicians. So there's one equation that I just got from kind of going through the motions of what it's asking. Piece of wire gets bent into a circle. Oh, I see that the perimeter is x. So I'm going to write that equation, x equals 2 pi r. Now let's express the area. The area of a circle we know is pi r squared. So now we want to know what the area is in terms of x. So I come back over here and I go, okay, well, I have the area in terms of r. I want the area in terms of x. So I need to find out what r is in terms of x. So r in terms of x is another way. I'm writing it out so you can see it. Terms of x is the same meaning as solve for r. And if we do that, divide by 2 pi, we get r equal to x over 2 pi. And again, that's r in terms of, this is what r equals, in terms, the terms that make it up have x in it. So that's why r in terms of x simply means solve for x. So if we plug in that, we get x over 2 pi squared. And now we can simplify. We have an x squared in the numerator. In the denominator, the 2 squared, and that gives us 4. In the denominator here, we'll have pi squared. Well, we'll have pi in the numerator, so one of them would cancel, which would leave us with 1 left in the numerator, or in the denominator. Okay, example 4. Similar to what we had with the point relative to root x, but perhaps a little different as we're expressing the area of the triangular region as a function of x. So what does that mean? So first off, if we draw our diagram here, hopefully I'm not using up too much space, 25 minus x squared is going to be a parabola. It looks something like this. Our vertex is right there at the coordinate, I'll write as a coordinate 0, 25. And we want a point that lies in the first quadrant. Again, we're going to represent that point as x comma y, but x comma 25 minus x squared. Now, if the triangle that they're talking about is this triangle, any point on the parabola or any point in space can be drawn out by x comma y, which is the same as this point. This is the x displacement to get to this point. This is the y displacement to get to this point. So we know that length is x, and this height is y, 25 minus x squared. So now, there's our first, you can think of that as your first equation. We want to know the area of that triangle, as we know area is 1/2 base times height, but we want it as a function of x. So we write it as a of x, and now we want the base in terms of x, and we want the height in terms of x. Well, that's what we have over here. Here's the base in terms of x. So we're going to plug x in for b. I didn't put parentheses around that. I could have, though. For the height is 25 minus x squared. And now we simplify that. A of x equals, I'm going to distribute the 1/2 x to both of them. That would be 25 over 2x minus, I'm going to write this as 1/2 x squared, so standard form. And then, of course, we could rearrange the terms, but then we could also work with it in terms of the quadratic to get a better understanding of how the area of this changes as this point moves up and down the parabola. Next, two numbers are added up to 10. I'm just going to take two numbers that I don't know. X plus y equals 10. Now it says express the product of these two numbers in terms of one variable. So I'm writing p, the product, equals xy. But we want it just in terms of one of the variables. And let's go ahead and keep that simple and make it x. So if we are thinking as well, if we want that just in terms of x, we need y in terms of x. So we're going to come over here and we look, okay, well, how do I get y by itself? Oh, I'm going to subtract over the x, which gives us y equals 10 minus x. So therefore, this is what y equals. So I have x, and then I have 10 minus x. Distribute the x in, and you get 10x minus x squared.